Oh, here's.
The answer is yes, I think. Okay, so I'll get started, and I guess I want to make sure switching rooms doesn't kind of change the environment, because we thought the good thing about the other room was a lot of discussion. So I hope this doesn't stop any questions or discussion.
We all have to shout.
Yeah, it's kind of a, but this is like classroom where people sit back. But, so anyway, I'm going to talk about some things. There'll be a little bit of overlap with what Eric talked about, but from a fairly different perspective. So I'll talk about possible inertial range dynamics, and want to mention some collaborators, Steve DeBreinkoff and Craig Winters, who are former students, and Eric as well. So anyway, so everybody has seen things like this, mostly from looking at clouds and stuff. This is actually from the ocean, where some divers laid out dye and just watched it evolve. And I partly put this up because it's actually 40 years ago that this was done, just about the 40th anniversary of Wood's really nice experiments. And these are probably Kelvin-Helmholtz instabilities, although not necessarily. And my interest is not in the instabilities themselves, but what brings them about.
This is the ocean surface, or is it?
That's internal to the ocean.
Okay,
Yeah,
so
so they laid dye.
Down on the surface, so we're seeing?
Yeah, I think they're looking down at an angle on the dye. They laid it out in an area and just waited until these instabilities developed.
Thermocline or something like that?
It's in a density gradient, yeah,
Yeah,
where there's
okay.
significant density gradient.
To scale? What is the scale?
It's a scalar. Yeah.
What
Sorry?
is the scale?
Oh, okay, that's what I was gonna, that's one of the reasons I brought this up. So this is a side view, and these are a few meters apart, something like that. And in fact, that's an important scale that I'm going to be talking about, because there's an Osmodoff scale that comes into this that relates to these. It's about a meter, typically in the ocean. Sometimes a little bit larger, sometimes a little bit smaller, but on that scale, it's not like 20 meters or anything like that. So that'll be an important scale that comes up, and in the ocean, it's about a meter. And I think people are all familiar with this. You know, there's been a number of lab experiments and numerical simulations by like Steve Thorpe's, where people understand the dynamics of the Kelvin-Helmholtz instabilities. But again, I want to talk about why they come about, a possible explanation, at least one possible explanation. And I'm going to call that stratified turbulence. And that's what Eric was talking about a week or two ago. And it's an idea, I think it was first introduced by Doug Lilly, and it provides a pathway to turbulence, pathway to 3D turbulence. And it may apply in the atmosphere, oceans, estuaries, any place where it's strongly stratified, and I'll try to define what I mean by that soon. And so I'm going to, as an outline, I'm going to try to motivate this, show some results from numerical simulations, some scaling arguments that suggest at least an inertial range, but one that's different than people are typically used to seeing. And then I'll show some data from the ocean and atmosphere, and maybe draw some conclusions and some questions. So,
One could call it stratified three-dimensional turbulence, couldn't one? A three-dimensional stratified turbulence to keep it distinct from the layer-wise two-dimensional.
well, I think maybe, though, that the layer-wise 2D stuff is important in this.
Well, it's part of the story.
Yeah, I think it's part of it. Well, I think, but there is a three-dimensional aspect, but the three-dimensional aspect is what I want to call 3D kind of classical turbulence.
But it applies in the non-rotating problem. That's the other.
Well, I think
clear, isn't it?
no, I think the ideas apply. They apply less and less as you get into rotation. It's true. So it's clearest in the non-rotating case. That's right.
We've also got this term geostrophic turbulence.
Oh yeah.
Strongly
Well, that's
rotating, which
the.
I hate.
I know.
Because it kind of is too restrictive.
Yeah, the intent's to get away from. I mean, it's trying to identify this as opposed to geostrophic turbulence, 2D turbulence, 3D turbulence, and all. And so we picked up on Doug Lilly's description and decided that describes it best. And so.
Is it stratified high Rossby number turbulence?
You could, yes. Yeah.
This is moderate Rossby number.
Moderate to high, yeah.
Okay, stratified non-low Rossby number turbulence.
Right.
You're always talking about scales less than 1,000 kilometers, right?
That's right,
That's not
right.
the point, it's the aspect ratio and the, whether Prandtl's ratio is 0 and so on, you know, F over N, that sort of thing. It's not the absolute scale.
Right,
Yes,
that's right.
that's true.
Yeah. Anyway, that's the terminology that we're using. And there are two things I want to point out here. People are mostly familiar with this, but I'm going to talk about strong, stable stratification that inhibits vertical motions, so that kind of quasi-horizontal motions in some way are preferred, and it supports propagation of internal waves. So what I mean by it is the following. If I take as the controlling parameters in the problem, and U prime, that's an RMS velocity. L sub h is a horizontal scale of the energy containing motions. And from that, I can define a Reynolds number. I can also define a Froude number if I bring in the buoyancy frequency that depends on the density gradient. And of course, the Froude number can be thought of as a ratio of a buoyancy time to a fluid mechanical time scale. And if it's large, the effects of buoyancy are not very important. And if it's order 1 or less, the effects of buoyancy become very strong. And also, I'll talk a little bit later, I can think of it as a ratio of the Azimuth scale, which I mentioned was about 1 meter or so in the ocean, to this horizontal scale. And then what also comes in is a gradient Richardson number that tells us something about the local instability of the flow. So those are important parameters in the discussion. And so as we were just discussing a little bit ago, what I mean by stratified turbulence here is general atmospheric and ocean motions where the Froude number is small and the Reynolds number is large. And I'm not really considering rotation. I'm considering the Rossby number to be very large. Okay, so now what scales might it occur? In the ocean, I think we'll see that possibly it occurs from scales from about 1 meter or a few meters up to at least several hundred meters. And there's some evidence that it might occur up to into the kilometer range. That's kind of disputed right now. And in strongly stable atmospheric boundary layers, like nocturnal boundary layers in the middle of the night or early morning, there's at least some data that shows the Azimuth scale is about 1 meter, and we could see the stratified turbulence up to several hundred meters. In the upper atmosphere, it might be, I have no data, it might be that the scales range from tens of meters to into the kilometer range. And there's some arguments that Eric's making that it may go larger.
Does this mean the largest scale of the turbulence, or?
The largest scale of stratified turbulence.
Okay.
Above that, some other phenomenon is occurring. Okay, and the importance of this, and if it exists, and is that it kind of it controls the smaller scale turbulence. So the spectral energy flux would be controlled by the stratified turbulence. It leads to instabilities in 3D turbulence. Another thing down here is if one wanted to parameterize a smaller scale turbulence for a larger scale model, they could have to take this into account. So also it is important in problems like dispersion. Okay, so, and there's a number of instabilities that could come in. I think I'll keep going from that. Now there's been laboratory experiments that deal with this that have been carried out in a number of places. I think first were done at Flow Research, but some very good ones at USC and Arizona State, Toulouse and Grenoble, Eindhoven and some other places. And usually in the lab experiments, like a lot are done with an object like a sphere and just tow it down the tank. And the tank is usually stratified with salt. And in that case, behind the sphere, the turbulence is kind of three-dimensional. Usually the Froude number is large. But as the flow decays, the Froude number decays and the Reynolds number decay, which is an important thing I'll show in a minute. What happens is that as the Froude number decays until it's order 1, which is a couple of buoyancy periods, the flow kind of physics dramatically change. And you start seeing these quasi-horizontal vortices, and you kind of can watch internal waves kind of slowly oscillating. But now some experiments, things are done differently, like grids are towed, and in the Grenoble, they're vertical grids to try to eliminate more of the 3D motion. Anyway, the Reynolds number is not large, and so in most of the experiments, the Richardson number is high. And so the classic 3D turbulence doesn't really develop in those laboratory flows. And so one of the big issues is, what do we learn from the lab experiments, and do those scale up to the geophysical scales? So, I pulled out one particular sequence that Jeff Spedding had done, and he's done a lot of the best experiments on kind of a single-toed object. He does a sphere that's about something like this big in a tank that's about 1 meter wide and all. And so what he's done here is he's looking down on the flow and he's measuring vertical vorticity and then color coding it. And so you can see it developing in time. The first image is about 2 buoyancy periods, and the last image is about 50 buoyancy periods. So he watches the flow evolving in time. And these little A's and B's and stuff what he's doing is he's watching vortex pairing occurring. And as that occurs, the flow scale gets larger and larger. And so by late times, you can see that the scales are developing significantly. They're growing significantly. And these have shown in all the experiments where you look at the wake of an object.
So you had something that went across this from left to right, or
Yeah,
right to left.
yeah. So a sphere came
Created
along.
local vortices in a particular layer.
So what he's done, to explain it more, he's towed this sphere down a tank
Yes.
at kind of a high Reynolds number, at high as he could in it, and he
Right.
generates 3-dimensional turbulence. And what he's done, he's sitting at the top and he's doing PIV measurements. And what he's done is
So he has a laser sheet.
he's got a laser sheet, in this case, right through the middle plane of the wake. And he's measuring velocity and inferring vorticity.
Right.
Yeah.
Okay.
So he's making other measurements too. He has some vertical measurements and stuff as well. So,
From this particular view, we don't have any picture of a zigzag instability or anything like that.
no, although he has papers that describe it. But his Reynolds numbers are so low
Okay.
that, and when he looks at the vertical information, it's not clear there's any instabilities there. Let me show you why.
Yeah, also zigzag instability is obtained when you start from 2D flow.
Yeah.
Here you start from a 3D flow.
Right.
Right, I understand.
Right,
So
right.
we aren't getting any type of columns to start
No.
with.
For
Not
that,
at all,
you need to
not
start
at all.
with a columnar,
That's right.
Right.
Right. So now, one of the things he did just to show this, and this didn't come out very well when I copied it, this is a Struhal number that is inversely proportional to the horizontal scale of those eddies. And he estimates it goes down, this is NT, as t to the minus 1/3. The main thing is that the scales are continually growing in this.
Did you write on the board what you mean by Struhal number in this case?
Yeah, it's
Frequency.
1 over it's proportional to 1 over the width, the separation of the vortices, or the size of the vortices.
Okay.
So as the vortices grow, the Struhal number goes down, and it goes down inversely proportional to time to the 1/3. Okay.
1/3.
Yeah, so it's the some width in the flow, like the diameter of the sphere, divided by the separation distance of the vortices. Main thing in this is that they're growing.
Wait, you said the width of the vortices is going down?
No, it's the inverse of the width is going
The
down.
inverse.
Yeah. The width is going up.
Going
Yeah, I should show 1 over the Struhal number for Bob. So now the main thing about this is that they also made vertical measurements, and they measured Richardson number, and this is hard to read, but this is a local minimum Richardson number in their field of view, which is most of the wake in the horizontal, in the vertical. And what you see is that after a time NT of about, 12 is about 2 buoyancy periods. At 2 buoyancy periods, there's almost nothing in the flow that would be unstable. The Richardson number is pretty high. And beyond that, and that's the minimum Richardson number, and beyond that, it's even higher. So this flow, by this time here, is very stable from a Richardson number point of view. And that's one of the things that differs, how this flow differs from a geophysical flow, because you expect the Reynolds and Richardson numbers to be, Reynolds numbers to be much higher, Richardson numbers to be much lower. So
Why would the Richardson number be all that low in the geophysical case? It's often quite high, isn't it?
yeah, but it's, well, we'll see. Let me show you as we go along. But it's this shearing that continually, that I think can continually develop. These flows cannot have a Richardson number below a quarter or below 1 at later times, whereas a geophysical flow can, because the Reynolds number is so high. So I'll talk about that more. And if I,
Not billows in the sky, where you tilt suddenly and locally it's like the Thorpe tilted tank.
that's one mechanism. Yeah. The mechanism I'm thinking about, though, is more of a cascade from larger scale down to smaller scale. And so,
Oh, okay.
bring the question up again, though. So anyway, that was a lab in the field. There are a lot of regions, as we'll see, where the Froude number is small. If you look at measurements, look at the output from probes, usually you see internal wave components. So you see things that are pretty obviously waves. And that's like the laboratory experiments. Also, if you watch plumes, for instance, on a stable night, you see this horizontal meandering, and the meteorologists always talk about plume meandering. And that may be similar to the lab experiments, and in the field you see 3D intermittent turbulence, or the turbulence you see is not continuous, but it's intermittent, kind of sporadic. In the lab, when the Froude number becomes less than 1, you just don't see any 3D turbulence. And of course, these larger scale velocities are highly non-isotropic. There's no overturning in the larger scales, and that's qualitatively similar to the lab. So,
Probably don't get 3D turbulence in the lab because there isn't enough scale to get an overturning and get a 3D effect.
well, I think that the Richardson number is just low, and you can't generate turbulence.
Okay, fine.
Yeah.
And also because the Reynolds number is relatively low.
That's the reason. So I'll combine those together. In fact, this is it here. So if you do if you look for regions where the Richardson number is small and do fairly straightforward scaling analysis, you find that the Reynolds number the Richardson number being less than order 1 implies that the product of the Froude number squared times the Reynolds number has to be greater than order 1. And this is often called the buoyancy Reynolds number, or an activity parameter by oceanographers. And the scaling shows this goes like epsilon over nu n squared, which is something common to oceanographers. So it's really the combination of the Froude number and Reynolds number that has to be large. So in this strongly stratified case, the Froude number is going to be very small, and it's a square, but the Reynolds number then has to be very large for the Richardson number to be less than 1. And you get those, you can have that in the atmosphere, but you don't have it in the lab experiments. And there have been some nice experiments at École Polytechnique by Paul Biant and one of his students that demonstrates this very well with the zigzag instability. They form the zigzag instability, and it only breaks down 3-dimensionally when this is the case. So anyway, this kind of says order 1, but if you look at ocean measurements and lab data, numerical simulations, the number seems to be more order 10, and people like Bill Smythe quote 40, and kind of a number in that range. So what you get is just this kind of a cartoon that shows you the Froude number, Reynolds number space now of the different types of things that can occur. So high Froude number means weak or no effects of the density stratification. And so there we have the usual case. If I go up in Reynolds number, laminar flow, some critical value, turbulence and laboratory turbulence, and high enough Reynolds number, you get into Kolmogorov type of turbulence. But as you come down in Froude number to where Froude number effects become strong, going to higher Reynolds number doesn't really mean that you have instabilities and turbulence anymore. And this line here is a line of constant value of this parameter. I think I'd put it at 10, but it's kind of an arbitrary value. It could be a little larger or smaller. But the thing is that in the most of the lab experiments and in most of the numerical simulations, they're down in this range. Whereas the geophysical problem is up here in this range. So there's definitely a difference, and raises the question again of what can we learn from these lab experiments and numerical simulations?
Would that include the recent simulations by Eric?
Okay, so that's the thing. Eric and myself both are trying to work in this range here. So I think that scaling analysis is something that Steve DeBreinkoff and I did to guide us in how to do the simulations.
Well, let's say this again. What we're looking at is above or below this line.
So we're looking at stuff up here. Very high Reynolds numbers, low Froude number, so stratification is strong.
Right.
High Reynolds number, so that we're in a region that can be unstable. Okay? If the Reynolds number is too low, then we're in a laminar flow regime. And
All
that,
the experiments you just showed us are above this blue line.
no, so the stuff that I showed with
Below.
Jeff Spedding was right here.
Oh, so now we're going to go above the line.
We'd like to go above here because that's where the atmosphere and ocean are.
Right, okay.
Okay. So now kind of as Michael was suggesting, now there's some scaling arguments that suggest, and they were proposed before these. Doug Lilly in I think a very useful paper in 1983 that suggested that when the Froude number is small, that the flow is kind of adjacent horizontal layers that continually decouple. If they decouple, then that means the shear increases, which means that the Richardson number decreases, and if that continues, there are going to be regions where the Richardson number is low enough for instability to occur. Now, Paul Bion and Jean-Marc Chumaz kind of looked at it a very different way. They first did instability theory and came up with this zigzag instability, and they concluded a similar thing, that no matter how strong the stratification is, that you can get instabilities occurring because the flow wants to decrease in scale in the vertical as much as possible. So both of these arguments tend to say that you can have strong, stable stratification, but if the Reynolds number is high enough, you'll get small enough vertical scales, you'll get small vertical scales continuing to develop, and so you can have local instabilities and turbulence. So no matter how strongly you stratify it, if the Reynolds number is high enough, it can be turbulent.
Is it really classical 3D turbulence?
Well, it's Kelvin-Helmholtz instability, if you call that classical, or maybe some other type, Humbo or something like that, instability. So
The whole thing is you have energy flow from a large scale to a small scale by
And-
some means.
And I think yeah. So these raise the questions about what are the dynamics in a region where you have the Froude number is small and the Reynolds number is large. And now Doug Lilly, even though he had argued that this instability would occur, he looked back at the lab experiments and said, well, in this process, the scales should grow. And in fact suggested a reason that there is a minus 5/3 in the atmosphere. On the other hand, a little bit later, just a few years later, motivated by Lilly's paper, Jack Herring and Olivier Mattei did some simulations that suggested that once you put the three-dimensionality into the problem, it'll cut off the upscale transfer and stop that altogether. Although it was a very limited simulation, that it suggested that. And so it's been a kind of a point of controversy. So that's a big issue. And then this issue of, do the laboratory and these numerical experiments scale up? What do they tell us about the atmosphere and ocean? So that motivated, I think, stuff that I've been involved in, and also the stuff that Eric's been involved in. Maybe he came at it from a different direction of he was looking at this large-scale atmospheric data. So I've done some numerical simulations, 3D time-dependent Navier-Stokes equations with the subject to the Boussinesq approximation, and I'll talk about that here. I have some others, but I'll mention these. So we have uniform stratification, no ambient shear, and what we do is we consider flows that start off at low Froude number. So kind of we avoid the first part of the lab experiment and just start the flow off looking a little bit like what the wake flows look like. But so we get as high a Reynolds number in the beginning as possible. So I've been involved in initial value problems, and then Eric has been involved in some forced turbulence, driving it to stationarity. The stuff that I've been involved in is direct numerical simulation, and Eric has done sub-grid scale modeling, although he's done some direct simulations later on. And the stuff I'm going to mention, I'll probably only have time to talk about the Taylor-Green. What we do is we start out with a Taylor-Green flow with some noise on it. And it's kind of a little bit like the Kármán vortices. Well, it's a little bit like more of a grid turbulence, like the Grenoble experiments. But we also have done some where we've set up a kind of an array of these Kármán vortices, like in Jeff Spedding's experiment. But I'll just show you the Taylor-Green, I think. We start out with no initial density perturbation and just let those flows go and see what happens, and do it at different Reynolds numbers and different Froude numbers. And so here's kind of one example where this is actually kind of a lower Reynolds number case, where you can see the initial conditions are this Taylor-Green type cell pattern. The motion is initially only horizontal except for a little bit of noise and no density perturbation. We let that evolve in time, and we start seeing shear developing for sure. And in our case, we see some weak transfer upscale. So now we've analyzed this in many ways, but this maybe is one of the more meaningful. So if we take our simulations and do horizontal averages of the shearing of the vertical shearing of the horizontal motion, or the square of that, we just plot that versus vertical direction, and we get the following. And this is now a flow that's decaying in time, and it starts out with the shearing is a Taylor-Green shearing, and it has this average, horizontal average peak value is about 0.25. Now we just let that go, and the shear just starts to take off tremendously, and it reaches its maximum at a time of 20. And this flow, again, is decaying, strongly decaying. But it reaches a maximum for this nominal Reynolds number 6,400 in terms of the Taylor-Green scales and the viscosity we use. This is like over 30 times the initial value. And it's easy to show that this peak value here is proportional to the Reynolds number. If we go to 12800, which we have, it gives us a peak value out here, so that the higher the Reynolds number you go, the stronger the shear you get.
Look at the red curves. Every single one of them has a big negative peak.
Yeah, so there's a subtle thing going on here.
Yes.
So this starts growing, and at first I thought, well, I'm going to see the strongest shears growing where the Taylor-Green shears are. But that's not what happens. The strongest shears grow in the region where the highest velocity is. And that's at the minimum of where the strongest shears are. And so what you see is that these shears are starting to grow in these regions, and that's where you see the peak values. So it's a little bit like Lily's idea. If you have a strong flow and it starts to decouple, you'd expect to see the strongest shears where there's the most velocity and not where there's originally the most shear.
But I'm saying there's a reversal.
Well, that's, yeah. So the minimum is, see, the first at time of 10, there's still a slight minimum where there was a minimum in the shear, but you can already see it growing on both sides of that minimum. and then it grows to a very large value here where the peak velocity is. You see what I mean? So,
I mean, it'd be interesting to know whether that shift is because of vortex stretching in these areas that sort of pulls it out one way and then pulls it the other, or is it a viscous effect where
I
the
think
shear
it's-
on either side gets?
I think it's not a viscous effect at all.
No, I doubt
No.
it.
I think it's the fact that if you think of the Lilly explanation or possibly the zigzag, you would expect to see the largest shears where you have the largest velocity.
Right.
And the largest velocities are right here, where there's the minimum in the Taylor-Green shear.
Does the unstratified Taylor Green,
That,
what does that look
yeah,
like?
I should have brought that up in the beginning. If you let this go unstratified, it becomes 3D turbulence. In fact, that's what Steve Herzog and others used initially to try to generate.
You don't get anything like this.
No, so the stratification really changes the problem. So this flow without the stratification wants to become nice 3D turbulence.
So you have a 3D Taylor-Green problem that's oscillating over that several periodic wavelengths.
Right.
And then you have a random scalar field on top of that.
No, you have a linear density gradient.
And why in the different oscillations do you get different effects?
They are because this is the periodicity of the Taylor-Green flow
But your Taylor Green is horizontal only, isn't it?
and vertical.
Oh, you've got vertical velocity.
Oh, yeah. No, vertical,
Only
vertical variation.
variation.
That's right. Yeah, you need the vertical variation.
Like this.
But they would all be the same unless there was something else other than a gradient in Taylor-Green.
Whoops. Yeah, let me,
In the spectral code, they should behave the same. So you must have an initial another wave mode in there or a little bit of
That's a
random.
there's
Noise.
noise. Yeah, we put noise in.
Okay, you put
Yeah.
noise.
To break the symmetries.
Right.
Yeah.
Okay.
Because Steve used the symmetries to get very high resolution.
Yes, right.
Yeah.
Totally the opposite direction.
Right, that's right. Okay, so, let's see, going the wrong way. Yeah, so the shear is growing, that's for sure. And to me, in a way, Lily's explanation was right, although it also could be the zigzag. Now, so we've looked at a lot of statistics, but I'll just show you a couple. And this is, we took these mean square velocity derivatives, squared them, averaged them over the whole domain now. So these are volume averages, and from that defined a volume average, Richardson number. And it turns out that the volume average for the initial conditions starts out at over 9. And if you look in the whole flow, there's no value lower than 3. So you look at this flow and you say, well, maybe it's stable because Richardson number is so high. But this three-dimensional motion wants to develop shear. And so the Richardson number just pretty dramatically starts coming down. And this is for 4 different Reynolds numbers. And so for this highest Reynolds number case, which is the one I'm going to talk about, this average Richardson number is well below 1 at between 10, 15, and 20. So this flow really wants to develop shear. And the Richardson number comes down. So you can look at the flow in different ways. And here's a visualization. And I'll talk about this one. So this is at a time of 20, which is what I'm going to be mostly focusing on, because even though the kinetic energy is decayed significantly, this is where there's the strongest shear, and it looks the most like there's some turbulence occurring. And so these are color contours of the local gradient Richardson number in 3 planes. There's a vertical plane and 2 horizontal planes, one that goes right through the high shear region and one that goes through a low shear region. And red kind of signifies the Richardson number is low, and blue signifies it's large. And the main thing about this is that in these regions of high shear, you see a lot of potential for some turbulent type events to occur. In the region of low shear here, there's almost nothing occurring. So we get this high shear developing in these layers, and the Richardson number is very low. And we can go in and look at the flow in different ways. It's kind of not that easy because you have large data sets from this. These are 512 cube simulations. And the one way we found that was useful to look at is to look at the vertical velocity. Here's a kind of a color-coded or gray-coded contour of the vertical velocity in a horizontal plane. And a small part, the domain size is 2 pi in this case, so it's about 13 or so. So this is kind of a section of the flow. And you see a lot of details of things going on here, but if we cut through a plane like this and make a vertical plot through that plane, which is shown here, now this is of the density field, we can see, Kelvin-Helmholtz type of things trying to occur. So we see kind of packets of instability, and if we had time, I can show you a weight calculation where you can kind of follow one of these in time. And so we see that occurring kind of intermittently. Now, a scale that I think is important is the Azimuth scale in this problem. And so and thinking of the possibility of an inertial range that I'll be talking about, and if I use kind of Onsager type of arguments, and so I define a kinetic energy for each wavelength and a potential energy for each wavelength, and then look at the wavelength where the two are the same. That winds up being the Azimuth scale. And the interpretation of it is that if you have horizontal scales that are smaller than the Azimuth scale, they have enough kinetic energy to overturn. And so they're going to start acting like usual turbulence. If you have scales larger than the Azimuth scale, they don't have enough energy to overturn, and those are going to remain kind of quasi-horizontal in motion. So now, partly the reason I bring it up is that when we started looking at spectra, here we saw the following. So this is a spectra of this one case of 6400 was showing, and this is horizontal kinetic energy versus horizontal wave number. And you can see the initial condition is this solid line, which is the Taylor-Green scale is 1 in the scaling. And then this stuff here is noise. So it's the Taylor-Green plus noise. And we just let that go. And we see a little bit of energy going upscale, but we see a tremendous amount of energy going downscale as well, as this spectra broadens out. And this dashed dot line here, it's fairly flat, and that's at the time of 20 where the smaller scales are most active. And there, one of the things we see is something close to a 5/3 range for about a decade or so, starting at the scale we put the energy in and ending at about the Azimuth scale. And when we wrote this, we just remarked that that was the case, and maybe there's some arguments for it, but it wasn't too convincing to us.
Jim,
Yeah.
where's the N over U scale in that?
So N over U is about, it's actually a little bit larger than the Azimuth scale.
Very
It's somewhere, somewhere there.
The unit of time is n minus what?
The unit of time here is scale in U and L. So the velocity and the length scale of the Taylor-Green mode.
So it's U over L, so it's kind of adjective time scale.
Yeah, it's an effective time scale, right?
Okay, it's not.
Right. Yeah. So we weren't too confident it seemed of interest. Now, Eric came along and was very strong about this, and so this is one of his plots. Now the spectra have been compensated, and now he's continually forcing it about here, and then he has a subgrid scale model about here. And he gets, very nice looking minus 5/3. So this is the scaling that you would expect that I'll talk about a little bit more. And in fact, he gets a constant out of this of about 0.51. And in fact, for turbulence data, for 3D data, you expect 0.4 or 0.5. So it's not that far from it. If we take his constant and just replot our data, it actually fits in, not too bad. So to me, it's kind of amazing that there's two calculations that are significantly different.
What's the constant so you're showing something like the k to the minus 5/3 spectrum,
Yeah.
and you're getting, what type of constant is this?
So essentially, this is compensated by the horizontal wave number and the energy dissipation rate. And so it's the constant that sits in front of the, the Kolmogorov
Kolmogorov law.
expression, yeah.
These are 1D spectra,
Yeah,
so if it was isotropic homogeneous, we expect the value of about a half.
yeah. I think they quote 0.4 sometimes, 0.5, I've seen higher than that, but it's in that range, which could be miraculous or not. But
What's EK? Oh, one's the wave spectrum and one is the.
no, there's, you mean this, there's actually, you have to be careful now in that there's potential energy dissipation as well as kinetic energy dissipation.
Okay.
Okay.
Oh, one's the energy of potential energy.
Oh, sorry, yeah, I didn't explain this
Sorry,
well.
yeah.
Yeah, I should have explained this. So this is the kinetic energy law that you would expect. It's the same as Kolmogorov's, but the reasoning is totally different. We're talking about a flow that's very non-isotropic three-dimensionally, and the mechanisms for transfer, whatever they are probably significantly different. This is the potential energy, and this is the scaling that you would get from the Obukhov-Corson scaling. And because of the dimensionality, everything is the same. So both of those seem to collapse, and in fact, they both give about the same constant, and that's similar to what we get as well.
Sorry to be a pain with the same question, but
Okay, that's
is,
okay.
is the U over N and Osmondov scale in Eric's the same as, on that graph, the same as where it was on yours?
Yeah, I mean,
So, because you have it way over near the dissipation.
yeah, so
Does he?
actually, I haven't seen it on his plots. It's too bad he's not here to ask,
Yeah.
because he's also getting into the point where he's got this, the subgrid scale modeling and stuff too. Yeah. I mean, that's one of the questions that I'm going to get to is about this U over N scaling. I think that's one of the important issues.
And potential energy dissipation means, I take it, available potential energy dissipation,
Right.
something like mod grad density fluctuations.
Squared, yeah, that's right.
Times diffusivity, that sort of thing.
Yeah, exactly. Yeah. So that's an important part of the dynamics, so the potential energy. And there's an issue about potential energy as well in this. So anyway, so the argument you get out of this is that if you have strong stratification, that implies the ratio of the Osmondov to the energy scales, that ratio is small. So that gives you some separation in scales here. And you can see that in our simulation. It wasn't a tremendous separation, but it's about all that we can resolve. It's like a decade and a half or so. Now, if the buoyancy Reynolds number is high enough, what that implies is that there's separation between the Kolmogorov scale and the Osmondov scale. So there's some separation here as well, which is what you would need to get some three-dimensional turbulence to occur. The scaling arguments that we've used for a long time are that the dissipation rate's really controlled by the horizontal motion and this horizontal scale. And Eric has done some work on that to try to give some credence to that. But it's independent of N and nu, or the Froude number and Reynolds number. If that's the case, then energy is being transferred from these large scales down to the Osmondov scale at a constant rate, independent of any of the other parameters. And so all of Kolmogorov's arguments go through.
When you talk about cascade of energy here, you mean cascade of total energy? Potential
Yeah,
and
potential and kinetic, that's right. Yeah, so both, I could show either case there.
dissipation of both or dissipation of
This is just, I wasn't getting into that detail, but it's both really, because both, they're proportional to each other.
So it should be independent of RAD, of the how do you call it, the buoyancy or not?
That's right, yeah. Yeah. And one of the subtleties is being independent of N, I think. You can think of a very high Reynolds number and getting that out of the way, but N as well.
So how does that scaling for the dissipation is appealing, but how does the dissipation know about the large horizontal length scale of the system?
How does the
epsilon?
Yeah.
The epsilon scales,
yeah, so, well, I think that, in a way, the controlling time scale is the advective time scale. And
U
so,
dot grad horizontal.
yeah, or U dot grad horizontal is a key. But it's really the controlling time scale in this is advective. So these big layers are kind of advecting across each other. and that is controlling what's causing the dissipation. That's the thinking behind it.
That supports Lily's picture, really, isn't it?
Exactly, yeah. Oh, yeah. Supports that scaling analysis. Yeah, so in a way, I would not be as negative about Lily's paper as Eric was, because I think that.
Despite the fact Lilly claims it's a backwards instrument, backwards.
Yeah,
logic, yes.
yeah. I mean, he based it on the lab data, and I think he's wrong there. But I think he has a lot of the right ideas too. He has a lot of interesting ideas in it, and
Actually, Lilly came up with some scale equations,
right.
which he speculated would give you a backwards energy, but which actually don't.
That's right. That's exactly right. That's
So
the
the
thing.
equations may be right, but his speculation was wrong.
Yeah, I think that's right. He looked at the lab data and said, well, it should do the same thing. But now, when we look at it more carefully, these are low Reynolds number, very low Reynolds number lab data. And this issue, again, of do those results scale up to the geophysical scales? Probably they don't. And in fact, that early simulation that Jack Herring and Olivier Mattei carried out kind of suggested that they don't.
No, and also concerning lab data, we have to be careful because when you do visualization, you see an increase of structure. But in fact,
I know.
just the selective decay by
Yeah.
viscosity is enough to produce an increase. In the experiment we did in Grenoble, we clearly see a very strong energy decay. So we don't get
Right.
the Caminus-Pfeiffer spectra, but still the scaling, the
Still,
derivative of energy is in U cube over L. We
It's
get
probably
it on
good.
a large scale. We get
Yeah.
exactly the same scaling than 3D turbulence
Yeah.
in terms of
Yeah.
energy decay, global
Okay.
energy decay. We are not able to get it in the
Yeah.
cascade, but at the
you still look
larger
at the same
scale,
scaling, yeah.
we have
Yeah.
exactly the same
Okay.
way.
Plus,
So-
you said you might have some higher Reynolds number data too.
Yes,
Yeah.
but the data that
Yeah,
we
but
published,
yeah,
these are
yeah,
produce exactly the same kind of energy
Right.
decay and 3D turbulence.
Right.
The derivative of energy is in U cube over L.
yeah. So from our point of view, it's probably your Reynolds number is a little bit too low, and so your spectra are fairly narrow, but
Yes.
the physics are very similar.
In particular, when you introduce rotation, you see a very clear difference.
Yeah, Yeah.
When we have the rotation
Yeah.
in the same experiment, we put rotation, and then we
Yeah.
get no energy decay with the same experiment.
yeah. There's a,
And we clearly see a very different
Yeah.
regime.
yeah, you have this effect that strong stratification tends to make things layered. Strong rotation tends to do the opposite. Kind of,
Jim, actually, to carry on the discussion, it's, you're, since you're doing decay,
yeah,
you're going from the Reynolds buoyancy, Reynolds number being in the nice regime.
Yeah.
Really, if you wait long enough, they
Right.
cross into it. So do you see any massive change in all these things?
you know, there's one plot I had in there that I could have. Let's see. All I see actually our final time where the flow has decayed a lot. This minus 5/3 is roughly maintained. But
It doesn't look any different.
yeah, it doesn't look that much different. But we haven't really, looked at it that much. This is kind of a short. This wasn't a real long study, actually.
Excuse me,
Yeah,
ask about the epsilon.
right.
Could you go back?
See, which way? This way. Here.
The epsilon may be measured by dissipation and flux.
Right. So this is
And the epsilon
this
may
is
be measured by third order structure function.
right. So that's one thing I'd like to do actually, because this is just the actual exact dissipation rate averaged in the domain.
So in your previous slide, you said C, about half. Could you go back? Yes, that one.
This one, yeah.
What is the epsilon? Is it measured by dissipation or?
Yeah, this is measured by dissipation. Yeah,
Maybe
yeah.
my question is it close to the one measured by structure function?
Yeah, Eric might have, but I haven't looked at the structure function. And I think that's really a good point. I think doing that type of analysis for this
So
flow,
it may tell the direction of
yeah,
cascade.
Yeah, well, I think it's clear that the cascade's going downscale because the energy shows up there. But I think doing that type of analysis for this flow would be very useful, especially looking at the vertical as well, because the one thing that we don't have is good information about the vertical structure. The layers aren't thick enough to get good statistics. So let's see. So, I mean, what comes out of all of this, if you have low Froude number, high Reynolds number, high enough buoyancy Reynolds number, is that you get these relationships which are the same as Kolmogorov and Novikov and Corson, but for very different reasons. There might be some other things that you could conclude as well, like there's a lot of ocean data that shows T-cube growth of patches and stuff. And so it's possible, for instance, that would occur, but I'm not sure because I think there are other mechanisms that go on in spreading of plumes. In particular, shear dispersion might be important. Anyway, I think in a way, if you go back and look at buoyancy subrange ideas, I think this replaces it because I've never felt very good about buoyancy subrange. So anyway.
The trouble with the buoyancy subrange was it's sort of homogeneous turbulence idea. wasn't it?
Isotropic.
The real thing tends to be very patchy.
Well, it's homogeneous isotropic even.
And even isotropic.
Yeah, it just
Yeah.
has problems. And so there's, I'm starting to build up some information, some other data sets. I'm still not convinced of all of this, but I think there's a strong case to be made right now. And so let me show you some geophysical data. And the first is by Jody Klimak, and he and Jim Moon did some experiments in a boat near the Hawaiian Ridge where they were kind of towing this device that was measuring temperature and velocity and things like that. And so this is a cartoon that he did, and then I'll show you the data. But I think the cartoon explains a lot. In fact, I'll show you some data from another experiment that Pascal Beret-Overtot and some others were involved in, and their interpretation now is similar. This is vertical spectra of, in this case, it's shearing. So it's k squared times energy, and it's from an older paper by Gargett, but I think this is still the accepted interpretation. And it goes as follows. So this is vertical spectra now, not the horizontal. In the range below this minimum here, so it means that you multiply the energy spectrum by k squared.
And vertical means vertical wave number, right?
That's right. Yeah, so that's right. So it's vertical wave number spectra. And so at the higher wave numbers, you get agreement with kind of the traditional isotropic values. The minimum here is close to the Osmodov scale. And then for lower wave numbers, they interpret that this as saturated waves. It's a k to the -1 here or k to the -3 in terms of energy. Now what Jody did was he laid his field experiments on this. And now I'm looking, the dark lines are horizontal wave number spectra, the same quantity. And what he found was that in the horizontal, this k to the -5/3 if it was energy carries out much farther. These are 2 decades right here. It carries out a couple of decades farther than the minimum in the cases that he saw. In fact, it was out to like several hundred meters in some of the cases. So his data are in the next, one of the sets of his data are in this here. So again, it's multiplied by k squared. But he sees, he was getting spectra going out to like 300 meters, and he was interpreting this as inertial convective subrange, which is probably impossible if you take the traditional case. It's not isotropic, it's affected by stratification and all that, but it is consistent with this idea of stratified turbulence. So he gets things from in the scale of a meter out to hundreds of meters. In some cases, this is one of his most active cases. Some of the time he doesn't. So one of the things I find is that some of the sets of data we see are consistent with it, some are not. now I started looking around more, and there's some very good data taken by Terry Ewart a while back in '76, and he had a vehicle called SPURV. It was a self-propelled underwater vehicle that had some good instrumentation on it, and he measured temperature. And he was looking for this part of the spectra, actually. This is the Garrett and Monk part of what's thought to be the internal wave spectra. But what he didn't look at was this part down here, and he had 15 sets of data that were at about 5 different places and about 3 different depths. And about, I think it's 12 of that set look pretty much like this. 3 of them don't. So there's, but when I draw a minus 5/3 line through these, it doesn't look too bad from about 1 meter up to hundreds of meters. And so these, you know, the number of these sets of data seem to indicate, well, maybe that's the case. And as we looked around, working with Eric, a paper came out by Holbrook and Fair, and they were also claiming an inertial convective subrange, thinking, of course, in an Obakov, and they're going out, these are in cycles per kilometer now, they're going out well above a kilometer, claiming a minus 5/3 range in the horizontal. And this is from acoustic measurements of displacement. So there's a set that at least is consistent, and I think at least their interpretation has to be wrong. There's no way that it can be the classical inertial convective range. And then this is the one by Pascal Bréau-Verteau and Von Herren and Lalonde. And they had a chain, a moored chain in a canyon west of Scotland, and we're making measurements there and used Taylor's hypothesis to infer horizontal spectra. And in fact, they wind up getting a number of the spectra in the range of about, their measurements were good from about a few, maybe 10 to 50 meters up to several hundred meters. And in that range, they see a lot of decay of like 1.7 and things. And so their interpretation was in the paper was very similar to how we might interpret Jody climax, or even the Terry Ewart's data. So they look the same, at least in a lot of the cases. And then one set of atmospheric data, I'm in communication with somebody else that has some upper level atmospheric data, but I haven't been able to read it carefully yet. But this is from Rod Freelich, who's at CU, University of Colorado in NCAR, and does field measurements. And so he was in a very stable atmospheric boundary layer, and where he had a moored balloon, I guess, holding an instrument chain. And this measurement was made at about 10 meters height and about 10 meter per second wind. And so this is a measurement of the temperature spectrum. And so we put in the Osmondov scale here, and he's starting to buy this interpretation. His feeling is that this is kind of your traditional kind of, I guess this would be Obakov-Corson subrange. And then this part up here could be a stratified turbulence range.
This is called Taylor hypothesis.
With Taylor's hypothesis, yeah.
Wave number spectrum.
That's right. So he got a frequency spectrum, and then
It's only a 10 meter height?
about 10 meters, yeah.
So it's a 10-meter height
Yeah.
above ocean plain.
Oh, this is atmospheric, it's flat ground, and
Grain fields in Kansas or something like that.
I can't remember right now. That's a good
Colorado
point.
somewhere.
It's somewhere where it's flat is all I can
Isn't
remember.
that big tower near Boulder, is it?
It may be, but I'm not sure. I should know. I
Very
should go back and look at that paper. It's a very stable night now, because they made measurements in nocturnal boundary layers that were a lot weaker in stability as well, and don't see this. But in the very stable case, this is what he's seeing. and this is temperature. I have these papers that I could pass on to you if you're
When
interested.
do they get, when it is less stable, they should get usual Kolmogorov?
It goes, well, they get, they don't see this and they see more usual stuff, and it goes more and more towards a usual boundary layer.
Not Kolmogorov, but
At the high wave numbers it is, yeah, but not at the lower wave numbers.
Excuse me, you said at high K, it's 3D,
Yeah, so this,
3D and on
yeah.
the left hand side, it's
so
3D.
to the right of the Azimuthov scale, this is his interpretation now. Now this is velocity spectra, the other one I showed was temperature. It goes along and he interprets this as the Kolmogorov range.
So the mechanics are very different,
Yeah.
but still same slope.
Yeah. That's why, is it a miracle the constant's the same?
yes,
Yeah.
it's strange because the wave number looks very large. So it is a scale corresponds to...
This is about a meter, it turns out. Yeah. Yeah.
Well, why it's not just Kolmogorov?
Well, it's gone into point. Well, this also I'm not sure what is going on here.
When you say Kolmogorov, you mean viscously dissipated at centimeter scales, don't you?
Yeah. So this is a meter. So here's centimeters and here's millimeters.
The instrument noise on the right.
Yeah, and he's probably down in the noise there. I'm not sure. I can pass this paper on to you, but this is.
Even the larger scale in the diameter is about a meter. Even the larger variable scale is just a few meters. No, the smaller scale.
So this goes up.
Yeah, yes.
He's making measurements up to. This is maybe, a decade, maybe 30 or something like
Still
that.
very small scale. I would expect to get some buoyancy.
Well, you might. I mean,
at larger scale.
yeah. Well, it's possible. I mean,
Our results over the ocean boundary layer at 10 meters essentially say this keeps on going
Yes.
until 600 kilometers.
well, that's consistent with what I'm saying, because the Azimuthov scale here is about 1 meter. Stuff doesn't turn over at much greater than 1 meter.
You were the trade winds, Bob, aren't you?
No, this is mid-latitudes. Trade winds is a completely different story.
Mid-latitude, what kind of weather?
We're talking about North Pacific Ocean. We're talking on most of the ocean surface, except when there's a strong, very strong low-pressure cell, because then the scatterometers don't get any measurements.
So you'll be emphasizing the windy conditions probably, won't you?
No,
Because that's when you see more turbulent energy.
no, I'm just saying the 10-meter horizontal spectra from 20 kilometers out to 600 kilometers is K to the minus 5/3.
Forgetting about clouds and stuff.
Yeah, forgetting about clouds. Well, I mean,
Yeah,
it
but that-
goes through the clouds.
yeah.
You see through the clouds with
Oh, okay.
scatterometers.
Okay.
The only places that there's no measurements are really intense local storms, because it churns up
Okay.
the ocean surface so much that the capillary waves
Okay.
can't be understood properly.
So it's a little bit like the Nastrom gauge data, where you
It
don't
is.
see it where there's storms, essentially.
Yeah.
Yeah. But I think Joel has a good point here, that this is 1 meter here, but this only goes up to maybe 30 or so, and it's not convincing that that's the case.
Can I follow up? I mean, that you've emphasized the minus 5/3, but what you're saying, which is semi-miraculous maybe, is that it's independent, the level's independent of stratification.
Yeah.
And
Well,
do you have any evidence of that, right? And boundary layers come in all kinds of different stratifications. We can talk.
yeah, it's just that you'd have to have some like bottleneck or some energy feed or something to change that cascade downwards to lift or drop the spectrum. Something's got to be going on there to do it. So, yeah,
So
Tony.
you have
Yeah.
an epsilon there, so you U prime cubed over L, and you say L is maybe 30 meters or something. Can you get a U prime and an L that, I guess,
Yeah, I mean, that's right. Now, of course, in the atmosphere, you go to bigger and bigger scales, and there's energy there as you go on up. There's no kind of minimum in the energy spectrum.
the U primes are probably pretty small then.
Well, so so I have some wind data there. So the mean velocity is about 10 meters a second, and U prime is of the order of like 50 centimeters a second, something like that.
Okay.
Yeah. I can't remember exactly what it is, but it's of that order. Yeah. Okay. I should have reread the paper before I did this. Anyway, this is suggested. I don't think this is a foolproof case by any means. I'm just saying there's some things that suggest it, and that suggest that it occurs some of the time. And if it's, and it has suggests different physical processes and stuff. But let me kind of go. These are things that I've talked about already. So there's a lot of open issues in this. And the first one is just what are the dynamics? If this range exists, there was a lot of discussion a couple weeks ago about the dynamics that occur in 3D turbulent inertial range in terms of vortex stretching and all kinds of other things. In this case, the vortex lines are, except in the very 3D turbulent regions, the vortex lines are mainly horizontal, and so the vortex dynamics are going to be very different. Another is what is the role of internal waves? For instance, there's a lot of potential energy that's a proportion of the kinetic energy in these flows, and are the density perturbations kind of slave to the velocity field, or meaning that they're just responding to the flow, or are there waves, or is that potential energy in waves that are propagating through?
You mean enslaved in the sense of balanced dynamics with
Right.
minimal wave activity?
Right, exactly. Kind of like a cyclostrophic adjustment.
It's more complicated than that, okay? Because waves, gravity waves, link the potential energy to the horizontal divergence, right?
Right.
So that's in the velocity. So
Right,
the velocity
right.
and the potential energy are maybe not the right things to separate waves and vortices.
Now we have a can of worms. Separating waves
Yeah.
and vortices.
Yeah.
Well, no, but
Well,
you gotta admit, even just the linear gravity waves, it's a interplay between the
yeah.
horizontal divergence
Yeah.
and
I mean,
the density
yeah.
fluctuations.
I mean, what I think is going on here in these particular simulations and Eric's are that the generation of waves by these vortices is weak.
Yeah.
And
then we can find the balance.
but if you go in the ocean, there's a lot of internal waves. If you go in the atmosphere in these cases, there can be a lot of internal waves. And so they can change the dynamics too.
No,
Or-
I understand that. Just
Yeah.
my point is,
Yeah.
the velocity field's got both the waves and the vortices.
Right. Totally, yeah. But I
the
think,
whole, the waves are generated by independent sources in the real atmosphere and oceans, aren't they?
right,
Spontaneous emission, vortex emission.
right. So, exactly. So anyway, then there's this question still, do the laboratory results scale up, or what can we learn from them? For instance, is there both upscale and downscale transfer in these motions? And there, what are the vertical spectra? And another is, that I think is a key, is this vertical scale of U over N critical to the dynamics? And because we're seeing simulation, it's not clear that it is, and we're seeing simulations coming out that Peter was talking about and some others where they use, there are more meteorological calculations of very large scale motions where this scale is well below the grid scale, so it doesn't exist on the flow, but yet they're seeing the similar regimes, although they're fairly narrow. And it's not clear that has to be resolved for the dynamics to occur. In fact, if you had to resolve that, to do a large-scale meteorological calculation, it would be pretty discouraging.
Okay, but in this sort of case, I think, the Coriolis effects are quite important, and so that will take over in terms of
Yeah.
the most important vertical scale.
Well, but I'm even thinking, say, 500 meters. Does a 500-meter horizontal flow worry about a several meter vertical scale?
Well, it depends on the time scale, doesn't it? If it's slow flow such that the time scale is the order of a pendulum day, then of course it'll be very different from this non-rotating case.
No, it's not. It's much smaller time scale than that. These flows are not that much affected by rotation.
You've got to be careful because the 2 pi and so on, it's just a few hours really.
Well,
It's twice the rotation and.
Yeah,
two
yeah.
on top of each
yeah, I guess, again, it's too bad Eric isn't there, but he did, he spent a lot of time looking at that and at least was convinced that over scales of, I don't, he mentioned that in his talk a week or two ago, that scales less than some number like 50 kilometers, I don't know what, something like that he felt rotation wasn't very effective. But,
I guess I'm sort of trying to be careful about this because
Yeah.
this is exactly what vertical scale it has is rather critical to this whole scenario. How much shear is it really going to get?
Right.
If there's a little bit of Coriolis that's, prizes
Right,
that apart
right,
a little bit
right, oh yeah,
beyond your tiny U, Z, O,
yeah,
then it could make a significant difference even if it wasn't dominant.
yeah, Yeah.
My work totally agrees with
Yeah.
what Michael just said. I mean,
Yeah.
even a tiny bit of rotation will set the vertical scale.
yeah.
And if you then let stratification go to infinity, you can have small vertical.
Say that again.
Vertical
So,
scales set by rotation.
I mean, even a small amount of, the point is
Yeah.
without rotation and at infinite Reynolds number, stratification is just going to collapse the
Right.
vertical scale to zero.
right,
If there's even a small amount of rotation, it will set it, that vertical scale.
yeah,
And then from that point on, it's a little different story from what you're
right.
I mean, one way to check the
Yeah.
point,
Well,
this is tiny scale, this UZ over,
E prime over
L-
N,
sorry, yeah, over N.
Yeah.
I mean,
yeah,
the L sub Z you're talking about, if you multiply that by N over F, that'll give you a horizontal scale at which you'll feel rotation.
right, right.
Yes.
And I think,
Multiply what by F over
Well,
N?
that's L sub
This.
Z.
L sub Z.
yeah,
L sub Z, you multiply it by N over F, so I guess I've got a U prime over F, so I'm talking about
you want to get a Rossby
computing
number
the
out of that.
Rossby number,
Right.
yeah, the scale at which
Right.
Rossby is 1.
Right, that's right,
Sure.
yeah.
And is that always so huge, really, in all these field situations?
I think the
think it
Rossby
is.
number is large
It
in
is.
those.
I'm saying that we only get this regime to start breaking down once you get up to that Rossby length scale. I mean, around 600 kilometers, where the Rossby deformation radius exists in the atmosphere at mid-latitude.
But that's the deformation radius based on a pretty
based upon-
substantial height scale, not that tiny height scale.
That's a good question. Why is that the appropriate length scale? Why, this LZ is between different shear layers, but maybe in the troposphere, the thing is, it's the layer height we're thinking about is the depth of the troposphere, some percentage of that. And maybe things will be different in the stratosphere. I don't know. That's a good unanswered question.
Yeah,
I
that's what
thought
I'm
you
saying.
were saying that this L sub Z was pretty tiny in the kind of cases you're talking about.
In the ocean cases, it's of the order of meters,
Meters.
yeah.
Yeah, so you need your Rossby deformation length based on those meters rather than, the whole height of the.
Well, in the ocean, it might be. I mean, we don't know how far out this scale goes in that this spectrum goes out into the ocean. I mean, you have measured, gave us measurements, for a few hundred meters out in horizontal extent?
Right.
Okay, so, other than maybe the salt layers that exist in the Caribbean or something like that, I can't think of any place in the ocean where you have a horizontal layer that doesn't extend, where there aren't significant variations in the height or something that would break that up after a few hundred meters. I mean, other effects are going to come in. But in the atmosphere,
I think,
the atmosphere could be.
yeah, I think the
You could
time.
summarize by saying if a given height scale, the ocean's about 10 times less wide than the atmosphere. Meters in the ocean would be kilometers hundreds of meters in the ocean would be kilometers in the atmosphere.
Yeah, maybe,
It's just a rough
yeah.
But I think that if you just get a time scale from these motions, like a meter per second, say, velocity in a 50 meter, like maybe 100 meter horizontal length scale, I don't think you get into hours, do you?
Right, I have another question. If we're imagining that this whole thing sort of, the shear layer between things sort of starts as a vertical vortex that has gotten pulled out like this by the
Right.
zigzag instability. Now, the zigzag instability is, as I understand it, is a single vortex that's doing something like this.
It's in a strain field, or you have a pair of vortices so each strains the other.
Right.
No, it's a perturbation on an initial vertical vortex in this.
But you need something else to strain it. If you just sit one vortex in the field, it won't do anything.
There's some work by Miyazaki that no one seems to cite, which is a single vortex in a large-scale horizontal strain field, and that goes unstable, I suspect, fundamentally similar way.
So the zigzag
Maybe.
instability isn't an instability just with initial vertical vortex.
You need something to strain that.
And a strongly stratified field.
Right. Yeah.
You need something else to strain it.
Yeah. Yeah. Colin has a
Horizontal.
question.
Oh, but going back to this thing about the vertical length scale, isn't that the vertical length scale of whatever's causing the epsilon? That's your dissipation. And that's the depth of the regions where the Richardson number drops to a low
Yeah.
value.
It's essentially the instability length
Yeah.
scale.
So,
That's right.
so what Peter's saying, if rotation is forcing that length scale to be bigger so that you don't have a region where the Richardson number drops to low value, I
Right.
could see that this whole mechanism could switch off.
Oh yeah, that can turn off. Rotation can turn it off.
Yeah, because what this does is
Yeah.
it's the mechanism by which you have whatever causes the epsilon. You have it,
Right,
that's what
right.
triggers the instability.
Right.
So if that doesn't get small enough to get you the local low Richardson number, and if that's what
That's right. That's right.
So that's the interest. That's a really interesting thing to do.
Yeah.
You know, like as you said, Paul and his student have looked at seeing these patches of regions where the Richardson number drops low. What happens if you tweak those simulations by just giving a bit of rotation? Do you switch off?
Yeah. Now Eric is saying that you don't.
Yeah.
But unfortunately he's not sitting there. He said that you add rotation, and you said you have to add a lot of rotation in order to switch those off.
Well, we said a lot of rotation.
Or whatever that means.
Well, yeah, I have to have him here to make it precise. Yeah. Yeah, but that's an important point. But I think the time scales, like I was saying to Michael, if you take a 1 meter velocity over a 100 meter scale, you don't get hours. Yeah, so I don't think those flows are going to be affected by rotation.
In fact, in the atmosphere, if you believe that the K-5 corresponds to this dynamic, it's clear. Since if you have K-3 at a larger scale, it's clear that the switch on of the rotation effect occur when you go from the
Yeah, that's what Eric.
K-5 to
Yeah,
K-3.
that's what Eric claims. Yeah.
So probably
Yeah.
What do you think sets up the initial shear that can go unstable? I mean, we have these different layers. In an experiment, it just happens, or your simulation, it started with an initial condition with the shear.
Yeah, it's got to be three-dimensional. It's a three-dimensional process, and just like in kind of maybe a simple way to think of it is the zigzag. So one of them is
But the zigzag I just heard, depended on an initial strain field.
yeah. What I'm saying is, if you look in a say horizontal plane, one of the vortices is straining the other one. You have to have this three-dimensional effect going on.
It's the zigzag instability. You start with a small initial perturbation in the strain field, and then the thing takes off and you get these separate layers.
You start with a small initial perturbation to a large flow. These vortices are sitting there like this.
So you have two vortices like this, you put
Right.
in a perturbation.
Right.
And then so it's two vortices. Are
Yeah.
they counter-rotating or co-rotating?
I think they're either one.
Either one. And you put in a perturbation, and then they start feeling each other, and they're going out and around each other.
But the main thing is they're straining each other.
They're straining each other.
Right.
Okay, then it makes a lot more sense. So you start with that produces, so now we go back to my question. We start out with these initial big, large vortices, and they've strained each other out so that each one looks like this,
Yeah.
and this one looks like this. Okay, they pulled each other out, okay? So you just have a single vortex for each one that's been pulled out. But then you take a slice through what you're showing, And we also have pictures in the atmosphere, and you get these Kelvin-Helmholtz billows. So each one of these has its own horizontal vortex that has been created out of a vertical vortex. But the Kelvin-Helmholtz instability between the shears is something with a series of these vortices.
Right, so what happens is that and I'm not sure zigzag instability is occurring in our simulation, but
Doesn't
in-
look like it.
in the- well, you'd have to diagnose it carefully, I think.
Yeah.
But it generates an instability on the scale of U over N. And so you have this shear on the scale of U over N. It's like a Kelvin-Helmholtz problem.
Vertical
That-
scale.
Vertical scale. Now it's like Thorpe's experiment, where you have this vertical shearing of the horizontal motion locally that has a scale of U over N. Now the Kelvin-Helmholtz instability winds up being about a factor of 10 or something larger in wavelength than that vertical scale, but you see Kelvin-Helmholtz instabilities occurring on that shear layer. And that's what they see if,
I mean, if you have two vortices in 3D and you put a perturbation around them, they will, by themselves, without any stratification, do something like this.
Yeah,
They'll
they'll
pull
go on-
each other out.
yeah.
Is this in some sense amplified by the stratification?
no, it's a different instability, clearly. Actually, what they were doing when they first found this was that they were doing airplane vortices.
Yes?
And so they pointed them up and put stratification in.
Yes.
And they found these new modes occurring. And these zigzag modes are totally different than, you're thinking of like crows or these other.
Yeah, right.
Yeah, they're just different modes.
They're different. So it
Totally.
is
Yeah.
it is an interaction between the shear and the stratification that amplifies the horizontal vortices in a different way than just
Totally
vortex
different.
stretching.
Yeah, it's totally different. Yeah.
I'm wondering if maybe this is the time to grab the last of the coffee and speak.